So I want to introduce a new.
Excuse me.
Yes.
Which site are we going to get the recordings that you have recorded?
So there's a recording I have sent to you, which is on email. I hope you have received it.
Okay, let me check.
Yes, just check your emails. It's recorded on Google Meet. So you have to log into your email, of course. Usually I have that class with another group, so I always record it on Google Meet. This one is always recorded on. Yes, this one is always recorded on this platform, MS Teams. So if you go to MS Teams, did you see the other? Have you ever seen the previous recordings?
No, I've just checked the one you have sent yesterday. Like I have seen it.
Yes, for the others, I think I told you that it's on. You can find it on MS Teams, or you can find them because we have a number of them. So if you go to MS Teams, let me see if I can demonstrate that again. When you go to your team, there's this tab here for files. When you click files, it gives you all the files that have been uploaded on this SCH303 team. So you have class materials. I have not uploaded anything there, or apart from the exercise, but I stopped uploading here because the rest is uploaded on SOMAS. And then we have the slides. And then we also have the recordings for the previous classes. Last week we didn't record because of the power problems. So I just chose to. That's why I had to send you the other recording. I think there's one here for this one where you have two. Excuse me. You should identify. I think one of them is faulty, but one of them is okay. So you can be able to identify which one is okay. Okay. So I want us to talk about chemical potential. So far we have looked at in our discussion on thermodynamics, we have looked at systems that contain only one chemical component. But you usually you can have systems that have many components, especially those that involve chemical reactions, and you have transport of matter. So what chemical reactions and transport of matter does is that there are some changes in the composition of those systems, since they have many components. So if you have A plus B giving us C plus D for that reaction, there are changes in the concentrations of all those species in that reaction. So therefore, for that system, you have to make some changes to the thermodynamic expressions that we have come up with. So for a pure substance and a system that has a constant chemical composition, this is the expression that we have for change in Gibbs free energy. So it's given by VdP minus SdT. Now in systems that have many components, where the number of moles of the various components are, say, N1, N2, and so on up to Nn, just an example, where these vary, further terms have to be added to the fundamental equation of free energy. So this equation has to be modified to take into consideration the number of moles of the various components. So we consider, for example, to do that, we consider G, that is Gibbs free energy, being a function of temperature, pressure, and then also a function of the number of moles of the various components, 1, 2, all the way to n. Okay. For this Gibbs free energy as a function of all this, the differential is going to be given by this. So it's quite a lengthy one. But if you look at it, you see that it's simply change in Gibbs free energy is given by delta G with temperature. So you have to differentiate it with respect to all the variables. Okay. And in this case, we have this number of variables here, T, P, N1, N2, all the way to NN. So, excuse me. First of all, you differentiate it with respect to temperature, keeping all the other variables constant. So Nj here represents the quantities of all components except one in the derivative. So in this case, you don't have one in the derivative. And then here you differentiate it with respect to pressure, keeping temperature and the number of components or the quantity of the components constant. Then you differentiate with respect to the quantity of the first component, keeping all the other components constant, and temperature and pressure. And then, of course, you also differentiate with respect to component 2, keeping all the others or the other variables constant, all the way to differentiate with respect to n, component n, keeping all the other components constant, and temperature and pressure also constant. So if the system does not undergo any change in composition, so that means the composition of each component is not changing. So what that means is that this dn1, or this is essentially changing component 1, this is changing component 2, all the way to change in component n. All these are going to be equals to 0, because if the composition is not changing, then the amount of a particular component, the change in the composition is going to be equals to 0. Okay. So if you do that, then this equation E68 is simplified in that if the dn1 equals to 0, dn2 equals to 0, all the way to dnn, all these terms are going to be equals to 0. So therefore, they're eliminated from this expression. So then this expression becomes dg equals to delta g over delta t at constant p nj dt. That was this first term, plus delta g over delta p at constant t and nj delta p. So now this one is simplified. Just give me a second. Huh? Now, if you compare this expression with this expression that we had come up with for a one component system, notice that there's some similarities. So like we have dt, we have a term times dt plus another term times dp. So essentially, when you look at this, we can equate the terms in that particular expression. So that is this particular term and this term, or that coefficient of that term, we can equate them. So this would be equals to minus s, and this one will be equals to v. Okay, so we are just looking at the fact that they are multiplied to dt and vdp. Then we look at this part of the expressions. So we say then these ones would be equals to the other coefficient of the original expression for change in g. Okay, so from these equations, that is these two equations up here, the total differential g in equations E68 can change. So this was E68. So we have changed this coefficient, we have equated it to something, and we have also equated this one to something. So now when we replace them, this expression becomes dg equals to vdp minus sdt plus change in g with respect to component 1, keeping all the other constants, dn1 plus dg over delta n2 with t, p, and nj constant, all the way up to change in g with respect to the composition of component n, keeping all the other t, p, and nj constant. Okay. Now the coefficient dn1 in this equation is called, the coefficient of dn1 is called the chemical potential, and it's given the symbol mu. So mu1 of the component, the first component. So this particular coefficient here is called mu1, and then this one is going to be called mu2, and so on and so forth. So this is called the chemical potential for that particular component. So in general, for a component, for an ith component, mu I is going to be given by this expression here. So change in the Gibbs free energy with respect to the composition of that component, keeping temperature, pressure, and all other compositions constant. Okay. So if we consider this as the definition for chemical potential, the expression, this E70, can be simplified further. Okay. Essentially, it becomes change in Gibbs free energy equals to VDP minus SDT plus the sum of all mu times dn for all the components. Okay. So the sum, in this case, in this expression, the sum includes all constituencies of the mixture. So this equation is very important. Sometimes it is referred to as the fundamental equation of chemical thermodynamics. So from the equation of chemical potential of a substance, so from this expression we can say that the chemical potential of a substance is given by the change in Gibbs free energy with respect to the change in the composition of that component, or the number of moles. So it's equal to the rate of change of Gibbs free energy of the system with the number of moles Ni of this particular component, when the number of moles of all other components are held constant. Okay, so that is the definition according to this equation E71. So chemical potential is an intensive property. And it may be regarded as a force which drives the chemical systems to equilibrium. Now, the fact that chemical potential of any substance in the system must have the same value throughout the system is an important equilibrium condition. So there's always a spontaneous flow of matter from one region of high chemical potential to a region of low chemical potential, just like the case of spontaneous flow of water from a high level to a low level, or spontaneous flow of electric current from a region of high chemical potential to a region of low chemical potential. Okay, so this particular situation is what now would drive a chemical reaction towards equilibrium. So the chemical potential may also be referred to as the escaping tendency of that substance. And the higher the chemical potential of a substance in a system, the greater will be the escaping tendency of the substance. And the opposite is also true. Okay. So we have established that dG is equals to VdP minus SdT plus the sum of all mu I dni, okay, in that particular system at constant. When you consider this particular expression at constant temperature and pressure, something happens. Change in, if it is constant pressure, then change in pressure is 0 because it's not changing, and change in temperature is also 0. So essentially, dG, we are eliminating the two terms. So dG equals to the sum of all mu I dni. When we integrate this expression, it becomes G equals to the sum of all mu I Ni. Okay. When you differentiate now this E73, notice that now we have two variables, mu I and Ni. So of course the differential for G in this case is going to be the sum of differentiating one and keeping the other constant, and then interchanging. So dg is going to be given by the sum of mu I dni. So in this case, you have differentiated ni, and the mu I is constant, plus ni d mu I, where mu has been differentiated, mu I, and ni has been kept constant. So subtracting equation E74 from E72, you get this expression here. The sum of Ni d mu I equals to VDP minus S dt. So this expression is referred to as the Gibbs-Duhem equation. Okay. At constant temperature and pressure, if only variation in composition is taking place, yeah, this equation is going to change. So constant temperature and pressure, remember these ones are going to be equals to 0. So essentially we are equating the sum of Ni d mu I equals to 0 at constant temperature and pressure. Now this equation, it shows that with variations in compositions, the chemical potentials do not change independently, but in a related way. Okay. Now, when you consider, for example, a system that has two constituents of compositions N1 and N2. This expression is going to become N1 d mu 1 plus N2 d mu 2 equals to 0, where T and P are constant. Now, if you rearrange this expression, you get d mu 2 equals to negative N1 over N2 d mu 1. So with this equation here, it is possible to find the change in chemical potential d mu 2 of the second constituent by knowing a change in the chemical potential d mu 1 of the first constituent that results due to the variation in the composition. So you see that the change in the chemical potentials are related. So they are not independent of each other. And this should be understandable when you consider that a particular reaction is taking place. Of course, if the variation of a reactant's concentration or of a reactant's chemical potential definitely would also affect the chemical potential of the other reactant. Now, in summary, so far, we have defined a number of thermodynamic functions. This is just a recap of all that we have covered. We have covered U, that is internal energy. And for that, we have this expression from the laws of thermodynamics, say du equals to dq minus dw. And then we have an expression for entropy, where entropy is symbolized by S. ds equals to dq reversible over T. We also looked at defined enthalpy, H given by U plus PV. We have also defined Gibbs free energy. It is G is given by H minus TS. And then we have Helmholtz free energy, which is also referred to as the work function. That is A, it's given by U minus TS. And then we have just defined chemical potential, that is mu I, and it's given by this expression. The rate of change of G with the composition Ni when T, P, and the Nj, composition of all other components, has been kept constant. We also defined heat capacity at constant pressure, that is Cp, and is given by the change in enthalpy with respect to temperature at constant pressure. We have also defined heat capacity at constant volume, it is Cv. It's given by the change in internal energy with respect to temperature, or with temperature at constant volume. So this is just a summary of the functions that we have looked at so far. Now we can think about the applications of chemical potential. Just a second. Now, applications of chemical potential. We can find the chemical potential of pure substances. So the chemical potential of a pure substance is given by this expression. Yeah. And it can be symbolized by Gi, where you have this symbol on top. Now, this is defined as the molar free energy of the component I in the system. The other partial molar quantities are going to be defined as, we can have the partial molar volume to be defined by this, delta V over delta Ni, and the partial molar entropy is given by delta S over delta N I. Now, from this expression here, from the expression dg equals to v dp minus s dt, you can have dg with respect over delta g over delta p at constant t equals to v. Okay. So here, notice at constant t, this one is going to change. This term is going to be equals to 0. So then delta g, no, I think I'm messing up. No, I'm not messing up. So this one becomes 0. So the whole term is 0. So from this expression, that is at constant temperature, we say the change in G with respect to pressure at constant T equals to V. And you can see how we end up to that expression from the rearrangement of this expression. Now, when you substitute the value of V that we have here, this one here, to this expression for the change in G with respect to pressure, so we can say this becomes delta Ni. So notice this one here, change in V with respect to Ni. So this is delta Ni of delta G over delta P at constant T equals to the molar, the partial molar volume for that particular component I. Or we can say d mu I over dP at constant T equals to Vi. So notice that we are saying we had said that this expression is what is the expression for mu I. Eh? So that's why we are saying this expression is the same as the change in mu I with respect to pressure at constant T equals to the partial molar volume. So using the similar argument, we can also end up with change in mu I with respect to temperature at constant P equals to negative partial molar entropy for that component I. So these partial molar quantities, they play an important role in the study of non-ideal mixtures. With the help of equation E81, for example, this one here, one can calculate the chemical potential of gases, liquids, and solids, provided the pressure dependence of volume is known. Yeah. Now, another application of chemical potential is in the study of phase equilibria. If you have two phases, that is one phase beta and phase alpha, and then there is a component I that is being distributed between the two phases, that is alpha and beta. So that means if component I is being distributed in the two phases, then you're going to have a change in the composition of that component I from one phase to another. So you can have D and I. So when you consider this substance I distributed between the two phases as shown, you can let mu I alpha and the mu I beta be the chemical potential of the substance in the two phases. And D and I can be the number of moles of I transferred from phase alpha to the phase beta at constant temperature and pressure. Now, equation 7E72, that was for DG. When you consider this, what is happening in the two phases, then DG is going to be given by, at constant, remember we had this DG, VDP minus SDT, and then plus the sum of all mu I D and I. So of course, at constant temperature and pressure, all these two terms are going to be equals to 0. So DG is the sum of all mu I D and I. So in this case, we have said this is the case. DG is going to be given by mu I beta minus mu I alpha D and I. So here we have a minus because when this D and I, when there's a change, the component is being distributed from, for example, phase alpha to phase beta, what is happening is that here you're going to have plus D and I because it is increasing. And here you're going to have minus D and I. So the sum of the two, of course, you're going to have positive mu I beta D and I, and then plus negative mu I alpha D and I. So therefore it becomes mu I beta minus mu I alpha D and I. So at equilibrium, DG equals to 0. And for a small finite change in the number of moles of I, D and I will be a non-zero value, okay? So therefore, if DG equals to 0, that equation, we equate this right-hand side of that expression to 0. It becomes mu I beta minus mu I alpha equals to 0. Essentially here, this is it's the same as equating mu I beta being equals to mu I alpha. So at equilibrium, at constant temperature and pressure, the chemical potential of each component must be equal in all parts of the system. So in the two phases, here now at equilibrium, what has happened is that now the component has been distributed in the two phases. So now there is no more distribution taking place. Now it is at equilibrium. So at that point, then the chemical potential of that component would be equal in all parts of the system, and this is a system that has two phases. Okay, so that's why we are saying mu I equals to mu I beta equals to mu I alpha. We can also use chemical potential. You can find the chemical potential for an ideal gas. Now, from equation E42, you can, this is way back, you can refer to this when you get the notes. The free energy of 1 mole of an ideal gas at 1 atmospheric pressure is given by this. Okay. G equals to G naught plus RT ln of P. So if there are n moles of the gas, the above equation is going to take this form. G equals to G naught, G naught plus nRT ln of P. So remember this, I think this expression was G equals to G naught plus nRT ln of P2. I stand corrected. You can confirm this, P1. So if this one was 1 mole, the pressure was not 1 mole, but 1 atmosphere, the initial pressure. So at pressure P2, then this would be the expression for G when you're having 1 mole. But when you have n moles, then this would be the expression for G. So then for n moles, you can divide throughout by n. So it becomes G over n equals to G naught over n plus RT ln of P. So therefore, the molar free energy or the chemical potential of an ideal gas is given by, so from this expression, you know that G essentially change in G with respect to N is the expression for chemical potential. So of course you can see where this is coming in. This is mu equals to G over N. So this expression, we can say mu equals to mu naught plus RT ln of P. We can find the chemical potential for, this applies for an ideal gas. We can also find the chemical potential in an ideal mixture. Just a second. So if you consider an ideal mixture, an ideal gas mixture, you have a system that contains, yes?
Yes, on chemical potential for an ideal gas, I've seen you saying that G is equal to G naught plus RT ln of P. What is the difference? What is the difference between G and G naught?
So G naught now would be the at standard conditions. We are talking at 1 atmosphere and 25 degrees Celsius. Okay.
Okay, fine.
So for an ideal mixture, suppose there is a system that contains this number of components, N1 plus N2 plus N3 and so on, moles of various ideal gases at any constant temperature T. You can let P1, P2, and P3 and so on, etc., be the partial pressures of gases in the mixture. So we are saying you have an undefined number. You can have up to 10 or even up to 5 or even just 3. So then for such a system, N, that is the total number of moles, is going to be given by N1 plus N2 plus N3 plus and so on. Then the pressure or the total pressure of that particular mixture is going to be given by P1, I think this is plus P2 plus P3 and so on and so forth. Yeah. Now from the ideal gas law V, what is the total volume of this particular mixture is going to be given by N1 plus N2 plus N3 and so on times RT over P, where P is the total pressure. Okay. So when you differentiate the volume with respect to the number of moles of any component, keeping temperature, pressure, and the number of moles of all other gases constant, we find this. With respect to component 1, V1 equals to delta V over delta N1 with temperature, pressure, and Nj constant is going to be equals to RT over P. With respect to component 2, delta V with respect to N2 with TP and Nj constant is also going to be equals to RT over P. So essentially we can write a general expression. It is VI equals to delta V with respect to Ni with Tp and Nj constant is going to be equals to RT over P. Okay. So this implies that partial molar volume of any component in a mixture of ideal gases is given by RT over P. So therefore, equation E81 can become Just looking for equation E81. Huh? This is equation E81. So it becomes d mu I over dp delta mu I over delta p at constant t and nj equals to RT over P. Okay. Because for equation E81, VI was equated to delta mu I over delta P at constant T and N and NJ. So therefore we are equating this to be equals to RT over P. So when we rearrange this, it becomes delta d mu I equals to RT. You have taken dp to the other side, dp over p. So of course this one, when you differentiate, it becomes RT dln of p. But then the partial pressure of a component I is given by the number of moles of that component divided by the total number of moles times the total pressure. So Ni over N times P. So for a given system, as Ni and N are constant, these are constants for that particular system, dln of Pi equals to dln of P, so that we can say d mu I equals to RT dln of excuse me. So when you integrate this equation here, we have mu I equals to mu I prime plus RTLN of Pi. So where mu I prime is an integration constant. So for that particular component I, this chemical potential at particular set standard conditions is a constant. Yeah, that is mu I prime. So this equation suggests that the chemical potential of any component in a mixture of ideal gases can be calculated from the partial pressure in the mixture. This is what we are seeing here. Equation E84 can also be written as, so this equation here can be written as Pi equals to Ci RT, where Ci is the concentration per mole of the component I. Okay. So here, mu I is going to be given by mu I naught plus RT ln of RT. Okay. Plus Ci. So we are replacing Pi into that expression here, this expression here, E84. So now the natural log of CIRT is the same as natural log of CI plus the natural log of RT. That's why we have them separate here. Okay. So mu I equals to mu I C prime plus RT ln of CI. This particular component here comes from a combination of these two terms. Okay. So that's why we are saying mu I C equals to mu I naught plus RT ln of RT. Now, from Dalton's law of partial pressures, in terms of mole fraction, we have Pi, that is the partial pressure, equals to P times Xi, that is the total pressure times the mole fraction of that component. So this Xi is the mole fraction of component I, and P is the total pressure, and therefore this E84 becomes this one here. It becomes mu I equals to mu I naught plus, so now we are replacing Pi with P times Xi. So ln of Pxi is the same as ln of P plus ln of Xi. So that's why we have here them being separated. Mu I equals to mu I naught plus RT ln of P plus RT ln of Xi. So now when you combine these first two terms, this is mu I for the pure gas plus RT ln of Xi, where this is a combination of the first two terms. This is the chemical potential of pure component I under the pressure P. Okay. This might seem a bit stretched, but when you get time and look at it, you'll be able to follow how we have arrived at all these expressions. So since Xi is always less than 1, or the mole fraction of a component in a mixture of gases, then its logarithm is negative. Okay, that is in this case here. Xi is always less than 1, so natural log of Xi is going to be negative. It follows that this particular expression, from that expression, that the chemical potential of any gas in a mixture is always less than the chemical potential of the pure gas under the same total pressure. So for that case, since this Xi is always less than 1, ln of Xi is going to be negative. So essentially we are saying that mu I equals just pardon my handwriting, mu I for a pure minus a quantity, let's call it, I don't know, C. So this is the expression, general expression from our understanding of the ln of Xi. So therefore, that's what the meaning of this statement. The chemical potential of any gas in a mixture is always less than the chemical potential of the pure gas under the same total pressure. Now, these similar considerations also apply for solutions. For a truly ideal solution, the relevant equation for the chemical potential of any component I in the solution is given by this. We have this expression here for a solution. So chemical potential for component I in solution is going to be given by chemical potential of the pure liquid plus RTLN of Xi, where mu I L is the chemical potential of the pure liquid and Xi is the mole fraction of the component I in solution. Okay, so another application of chemical potential, it can be used to find, you can find chemical potential of real gases and fugacity. We're going to see what that is. So for real gases, of course, we're going to have some corrections. We know we have just looked at ideal solutions and a mixture of ideal gases. But for real gases, you're going to have some corrections to the expressions. So just give me a second. Now, for the equation E83 for chemical potential is given by this: mu equals to mu naught plus RTLN of P. This is applicable to ideal gases. Now, for real gases, a new function is introduced, and this is called fugacity, symbolized by F. And it is defined by an equation that is analogous to E83. So in the case of real gases, we don't talk about the pressure, but we talk about the fugacity of that particular gas. So therefore, the chemical potential of a pure real gas is expressed as mu equals to mu naught plus RT ln of F, where F here is fugacity. So fugacity here is regarded as an idealized partial pressure, and it includes in it all the effects arising due to imperfections of real gases. Okay, for an ideal gas, the fugacity becomes equal to pressure. So for an ideal gas, F equals to P. Since any real gas tends to behave ideally when its pressure is reduced to zero, the definition of fugacity of any gas can be completed by stating in general that F equals to P as P tends towards zero. Okay. Or we can talk about the limit F over P equals to 1 as P tends towards 0. Okay. So the ratio F over P from this expression here is called the fugacity coefficient of a gas. And it is denoted by this symbol. It is a measure of the extent to which any real gas deviates from the ideal behavior at any given temperature and pressure. So in a mixture of real gases, the chemical potential of any constituent I is given by mu I equals to mu I naught plus RTLN of Fi over Fi naught. The ratio of the fugacity Fi to the fugacity in the standard state, that is Fi naught, is called activity. So that is activity Fi over Fi naught equals to Ai, that is the activity. So in terms of activity, the chemical potential is expressed as this. Mu I equals to mu I naught plus RTLN of Ai. Okay, so let's take around 5 minutes, and then we come back and talk about phase equilibrium. Just an introduction. We get into the introduction of phase equilibrium. Just take 5 minutes. Okay, let's get into this discussion on phase equilibria. Now, in phase equilibria, we have what we call the phase rule, which you're going to see very soon. This expression, F plus P equals to C plus 2, where F is the number of degrees of freedom, P is the number of phases, and C is the number of components. So this phase rule is a generalization which explains equilibrium between the heterogeneous system. Okay, that is F plus P equals to C plus 2. Now, the rule does not involve any assumptions as to the nature of matter and is valid provided the equilibrium between any number of phases is affected only by temperature, pressure, and concentration, and not any other force like gravitational, electrical, or magnetic force. Okay, so it applies. The only considerations here are temperature, pressure, and concentration. Now, first of all, you have mentioned a few things. We have mentioned what F being the degrees of freedom, P is the number of phases, and C is the number of components. So what are we talking about when we mean by phase? So phase is any homogeneous and physically distinct part of a system which is separated from other parts of the system by definite boundary surfaces. So for example, we can consider a system of ice, water, and water vapor. So here, each form, these are all forms of one thing, of water. Liquid water, we have ice and water vapor. Each form constitutes a separate phase. So here we have 3 phases, and it is separated from other forms by definite boundary surfaces. Just look at this. So for example, you have 3 phases. So you have the solid here. And then you have the liquid. And then you have the gas. So all these, they are boundaries for all these 3 phases. Yeah. So they are distinct from the other parts in this particular system. Now, every solid in a system is regarded as an individual phase, except in a solid solution, which is homogeneous. So in this case, maybe you have 2 solids that have been mixed. You can talk about salt and sand, and then they have been mixed homogeneously. So here you have 2 solids, but now they're homogeneously mixed. So in that case, this will constitute a single phase. The mixture of salt and sand, or the solution of salt and sand, is going to be a single phase, no matter how many chemical compounds it may contain. So this is the exception now. But every solid is usually considered as an individual phase. Now, the salt this particular salt, I think I've not been able to do the subscripts, but just take note of that. This salt constitutes a single phase. It's a solid, although it consists of two chemical compounds. We have the anhydrous salt and then water in it. But since it is in crystalline form, it is considered as a single phase. The same applies to a liquid solution. If you have two or more liquids which are completely miscible with each other and they form one liquid layer, this will constitute only one phase. But if the two liquids are immiscible and they are distinct layers, you have two layers. For example, in the case of benzene and water, they are immiscible. So when you mix them, eventually you have two layers being formed. So in this case, there are two phases separated by a definite boundary, and you can see this with your naked eye. And if there are three immiscible liquids, then there will be three phases in that case. Now, in the case of a gaseous system, it always constitutes a single phase, no matter the number of gases that it consists of, because gases are always miscible and they usually form a homogeneous mixture. So of course, at the beginning, when you mix two gases, it will not be homogeneous, but with diffusion, eventually you have a homogeneous mixture of the gases. So it's always a single phase in the case of a mixture in a gaseous system. So that was the definition of phase. Now, for a component, the number of components of a system at equilibrium is the smallest number of independently variable constituents by means of which the composition of each phase can be expressed either directly or in the form of a chemical equation. So for example, ice, water, and water vapor in equilibrium is a one component system because the three phases, the chemical composition is water, that is H2O. So then it's a one component system. So molecular complexity of water is different in the three phases, but the number of components is not affected. Another system we can look at is sulfur, a sulfur system. This is a one component system, although sulfur occurs in various forms. That is, you have the rhombic sulfur, you have monoclinic sulfur, you have liquid sulfur, and you have vapor sulfur. So each form can be expressed in terms of only one component, that is sulfur. So in the case of water, you have H2O. The only thing that you vary is either excuse me, just a second. So in the case of sulfur also, it has different forms, but all of them are sulfur. It's a one component system. Now a solution of sugar in water, this one is a two component system because composition of sugar and water must be specified to describe the system completely. So the system consists of sugar and water. So those are two components. But then it's a single phase. So for chemically reactive systems, the number of components, C, is determined by using the relation C equals to S minus R. Where S is the number of chemical species present in the system, and R is the number of independent chemical reactions which the various species undergo. So just remember, C equals to S minus R. S is the number of chemical species present, and R is the number of independent chemical reactions which the various species undergo. Now, if ions exist in the system, the condition of electron neutrality should also be included. And thus, for such cases, the equation is modified to become C equals to S minus R plus 1. Okay. Let's consider this this case here. A system where you have potassium chloride, sodium chloride, and water. Now for this system, there are 6 species. So first of all, you have KCl. But then in water, KCl forms potassium, and then chloride. Okay. The sodium chloride, that is. We have sodium chloride, which again forms sodium ions and chloride ions. And then eventually we have water. Okay. So we have 1, 2, 3, 4, 5, 6 species in the system. We don't consider the dissociation. We know that water dissociates, but we are going to disregard that one because it's usually to a very small extent. So the number of independent reactions, that is R. Remember R we said is the number of independent chemical reactions. We have two reactions that are taking place. We have the dissociation of KCl to form potassium and chloride ions. And then we have the dissociation of sodium chloride to give us sodium ions plus chloride ions. So these are we have 2 independent, so we have 6 species, and then we have 2 independent reactions. So therefore, for this expression here, C equals to S minus R plus 1. This is going to be equals to 6 minus 2 plus 1. So this equals to 3. So here, this is going to be a 3 component system. So that's how you determine the number of components in that particular system. You can also consider this particular system here. So this system, you have to consider what are the number of species. So of course, from this we get a chloride. From this and this we get a chloride. From this and this we get a bromide. And then we have sodium ion from these first two, and a potassium ion from these last two. So in real sense, for this system, we have how many species? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 species in this system. And then the number of independent reactions. So of course you have the dissociation of this. This will also dissociate. This will also dissociate, and this will also dissociate. So we have 4. Let me just do this. This is S, number of species, and this is the number of independent reactions. That is 4. So to get the number of components, C is going to be given by S minus R plus 1. So this equals to 9 minus 4 plus 1. So the number of components in this is 4. It's a 4-component system. In summary, we can say that for non-reactive systems, the number of components equals to the number of chemical species within that particular system. For reactive systems, the number of components equals to the number of chemical species minus the number of independent reactions minus the restriction due to the condition of electron neutrality. Another definition that we need to dispense with is the degree of freedom. That was, I think that was F. So the degree of freedom, F, the number of degrees of freedom or variance of a system is the number of variable factors, such as temperature, pressure, or concentration, which must be specified in order to define the system completely. So usually when you talk about a particular system, there are a number of variables that need to be defined for that particular system to be completely defined. For example, a system that has one phase like water vapor, define the state of this system completely. You have to specify the temperature and the pressure. Okay. So the system, therefore, you can say that it has 2 degrees of freedom, or is bivariant, because you need to specify the temperature and the pressure. Okay. When you have 2 phases in equilibrium, such as ice and water, only temperature or pressure needs to be arbitrarily fixed to define the system completely. Okay. So in this case, this 2-phase system, you need to fix one and vary the other for temperature and pressure. So the system has only 1 degree of freedom, because one is fixed, one variable is fixed, and the other is the one that can be varied. So it is called univariant. You can also have a case where you have 3 phases in equilibrium. For example, ice, water, and water vapor. Now, the existence of these 3 phases usually takes place at what is called a triple point. This triple point is usually fixed. Yeah. So it is at a fixed temperature and pressure. So that means there are no degrees of freedom. The 3 phases can only coexist in equilibrium at a particular temperature and pressure, which are thus these are automatically fixed. So this type of system is called invariant, meaning it does not, there is no degree of freedom. It has 0 degrees of freedom.